Hello viewers, today in this part of the discussion we will talk about interference by division of amplitude. The brief outline for the talk will be thin film interference, anti-reflecting films, Newton's rings, Michelson's interferometer. Thin film interference. Interference of waves from two surfaces of a thin film is due to division of amplitude. A plane wave is incident on a thin film of thickness d vertically reflected from a partial mirror, and let P is the photographic plate or the eyepiece. As you can see in the figure in this slide, the position P denotes the position of eyepiece or photographic plate. Let the crest due to the reflection from the upper and lower surface of film is represented by solid and dashed line. The ray reflected from the lower surface traverses an optical path of 2 nd, where n is the refractive index of the medium. The ray reflected from the upper surface will suffer a phase difference of pi. So, interference will be destructive if 2 nd is equal to m lambda, and it will be constructive if 2 nd is equal to m plus half lambda, where m is integers 0, 1, 2, 3 and so on, and lambda is the wavelength in free space. The amplitude of a reflected wave from the top and bottom surface will be different, but they can be same by adjusting the refractive indices of the medium 2 and 3. If the refractive index of medium 2 lies in between that of medium 1 and medium 3, then the condition of interference will change. That is, for destructive interference we need to satisfy the condition, that is 2 nd is equal to m plus half lambda, and for constructive interference 2 nd is equal to m lambda. These correspond to minima and maxima respectively. Now, if the incident angle is oblique, unlike the vertical incident angle that we had, then the ray reflected from the lower surface traverses an extra optical path. And what is the value of that extra optical path? And that can be calculated from the following figure. As you can see that we can show the extra optical path lambda is equal to n2 multiplied by BD plus DF minus BC, and this will eventually give us delta is equal to 2 n2 d cos theta prime, where theta prime is the angle of refraction, and this is called cosine law. Now, let us discuss about anti-reflecting film. This is a very important concept in optical devices for the day-to-day applications. A ray incident at a vertical angle from rarer to denser medium. Now, if we want to find out the amplitude of reflected and transmitted ray, then we can show that the amplitude of reflected ray can be denoted by the following expression, that is AR is equal to N1 minus N2 divided by N1 plus N2 into AI. Similarly, the amplitude of transmitted ray can be denoted as AT is equal to 2 N1 N2 divided by N1 plus N2 into AI, and AI is the amplitude of incident ray. Now, if we consider two conditions, that is, in the first one, if N2 is greater than N1, then the reflection amplitude will be negative. This suggests a phase change of pi after reflection. Now, the reflection and transmission coefficient can be written as R is equal to N1 minus N2 by N1 plus N2 and T is equal to 2 N1 N2 by N1 plus N2. If the ray is incident from denser to rarer medium, that is, if N1 is greater than N2, then the reflection and transmission coefficient become R prime is equal to N2 minus N1 by N1 plus N2, that is equal to minus R, and T prime is equal to 2 N1 N2 by N1 plus N2. Now, if we know the four expressions that we discussed so far in two different conditions, that is when N2 is greater than N1 and N1 is greater than N2, then we can find out the relationship which represents the final expression to achieve anti-reflecting film, and that is 1 minus T into T prime is equal to 1 minus 4 N1 square N2 square divided by N1 plus N2 square, which will give us N1 minus N2 square divided by N1 plus N2 square, which is equal to R square, and this is called Stokes relationship, which is very important to understand the concept of anti-reflecting film. On occasions when no reflection is desirable, often the surface would be coated by a material such that the thickness of the layer, that is, let us say it is represented by D, should be equal to lambda by 4n, where n is the refractive index of the coated material. This minimizes the loss in the medium. The refractive index of the material must be less than that of the surface material. So, following important points need to be remembered to get a better anti-reflection or better anti-reflecting film. The refractive index for coating layer must be chosen wisely for anti-reflection. In general, Ng is greater than Nf. The anti-reflection mostly works well for a particular wavelength, though it works fine for a broader wavelength as well. Here the energy appears mostly in the transmitted beam. Next, we will discuss a concept called Newton's rings. If a plano-convex lens is placed over a plain glass surface, a thin film will be formed between the lens and glass plate. As you can see in the image or the figure in this particular slide, AOB is the curved region of the lens which is in contact with plane POQ at O. The thickness of air film is 0 at the contact point and gradually increases to the sides. For a near normal incident of a monochromatic light, the optical path difference between the reflected light from curved and plane surface is 2 nt, and for path difference of 2 nt, where n and t are the refractive index and thickness of the film respectively, whenever the thickness of the film satisfies the condition, that is 2 nt is equal to m plus half lambda, one will get maxima, where m is integers, that is 0, 1, 2, 3 and so on. Similarly, whenever it satisfies the condition 2 nt is equal to m lambda, one will get minima. Since the convex side of the film is spherical, so the thickness of the film will be constant. the center of the film will be concentric at the point O. Now, the radius of the rings can be found out in the following way. Let Rm is the radius of mth dark ring having air film thickness of T. Then Rm square can be found out to be equal to T into 2R minus T, where R is the radius of the curvature of the convex surface. For T much smaller than 2R, we can have Rm square nearly equal to 2TR, or 2T is equal to Rm square by R. Now, using this for minima, we will get Rm square by R is equal to m lambda by n, or this will give us Rm is equal to square root of m lambda r for n is equal to 1. So, as the radius increases, the rings will get closer. In between the dark rings, there are bright rings, and the radius of these bright rings can also be calculated by using the figure in the previous slide. And if we do the calculation, we can find out the radius of the bright ring as Rm is equal to m plus half lambda r square root. As per the expression that we obtained for minima, the first spot at the center will be a minima or a dark spot. By using the diameter, it can accurately give us the information about wavelength, that is lambda is equal to d m plus p square minus d m square divided by 4 p r. One important application of Newton's ring is to find out the optical flatness of a glass plate, because if a glass plate is completely flat, then if we put a curved glass, then the formation of Newton rings will be equally spaced. The next thing that we will discuss is the Michelson interferometer. So, what is this Michelson interferometer? It is an interferometer which is used to distinguish very fine components of a particular wavelength. So, let us try to understand how the structure looks like. So, a light from a light source at S is allowed to pass through a plane glass L. It then incidents on a beam splitter G1, a part of which will reflect and the other part will transmit. Let there be two mirrors M1 and M2 which are perpendicular to each other. Mirror M2 is fixed while M1 moves towards or away from G1. A light emanating from point P will get partially reflected and transmitted by the beam splitter. The reflected beam 1 will be reflected from the mirror M1 and comes to the eyepiece through path 5. The transmitted beam 2 will be reflected from the mirror M2. This will be reflected from the mirror M2 and follow the path 4 to reach the eyepiece through path 6. The waves coming through path 5 and 6 will interfere the way explained before. Now, let M1 and M2 are separated from the beam splitter by a distance of x1 and x2. The rays coming through 5 and 6 would look like they are coming after reflection from two mirrors M1 and M2 prime separated by a distance x1 minus x2. For an extended source, if a camera is placed at the eye and focused at infinity, then the concentric fringes will be formed at the focal length. If the beam splitter is just a plain glass plate, then the wave reflected from M2 will have an abrupt phase change. Since the extra path that one of the beams will traverse is x1 minus x2, for destructive interference the following condition must be satisfied, that is 2d cos theta is equal to n lambda, where d is the difference of x1 and x2, that is x1 minus x2, and theta is the angle that the rays make with the normal to the mirrors. Similarly, for the condition of bright ring, the following conditions must satisfy, that is 2d cos theta is equal to n plus half lambda, where n is the integer values of 0, 1, 2, 3 and so on. Now, it can be shown that as we decrease the separation d, the fringe pattern will collapse at the center. So, if n fringes collapse at the center of the fringe pattern by moving the mirror M1 by a distance d0, then we must have 2d is equal to m lambda, or 2d minus d0 is equal to m minus n lambda. Here we have chosen theta is equal to 0. Thus, lambda is equal to 20 by n, and this provides a method to determine the wavelength of the wave. So, this can also be used to distinguish two closely spaced wavelengths. So, today what we understood, if we want to conclude that in nutshell, then we can come up with the following important points. So, these are like 4 to 5 points which are very important as takeaway points from today's discussion. First, we tried to understand the interference from thin films. So, what exactly the information that we can get from the interference patterns that we obtain from thin film? Exactly what we showed is that the interference from thin films is a phenomenon where the division of amplitude gives rise to the interference pattern. Then we discussed the properties and application of anti-reflecting film. So, we found that to obtain a anti-reflecting film, which basically tells us that there would be less loss from the film when a light comes and incident on the film. If we do not want any loss from the surface of the film in terms of reflection, then the property that we tried to understand from the concept of anti-reflecting film can be useful. So, we found that to obtain a anti-reflecting surface, we need to make the surface a little bit rough, and the size of the grain on the surface should be more or less equal to the fourth of the wavelength that is incident on the surface, that is it should be close to lambda by 4. If this condition is satisfied, then we can obtain a anti-reflecting films, and nowadays anti-reflecting films are very important because the day to day usage of car, when you are going somewhere in a sunny day, then you do not want a lot of reflection from the windshield. To achieve that, nowadays car manufacturers are coming up with a coating on the surface of the windshield in such a way that there will be less reflection from the surface and there will be no difficulty in the visibility of the driver. Then we discussed the formation of rings which are called Newton rings after interference from a curved surface on a plane surface. So, Newton's rings are a kind of hindrance when you want to have a completely plane surface and that plane surface is acting as a substrate for a curved surface. So, basically Newton ring concept is used to test the flatness of a plane surface. To obtain a flat surface, you have to ensure that there is no formation of Newton's ring when another flat surface is put on that testing of the flat surface. In this way, Newton's ring can help us to achieve a condition whether or not we have obtained a flat surface in our applications. Then the final concept that we discussed is the interferometer that was invented by Michelson and which is called Michelson's interferometer. And by using Michelson's interferometer, one can distinguish very fine wavelengths from each other, and which is the backbone of many of the spectrometers that we use in our research or R&D applications in various labs, where you want to distinguish two different wavelengths with a very small difference in wavelength, such that you can identify the wavelength due to a particular component in the medium, and you can say that this particular component is present by studying the absorbance spectra or the transmission spectra of the material. So, in this way today's discussion can help us understand many applications in much better way. Hope you would have liked today's discussion. Thank you very much.